Hello everyone, let us look at how do we couple light from the side. So, there are two ways to couple light. Right? So, we looked at the vertical coupling, but now let us look at lateral coupling. So, how light could be coupled from the side, the edge of the chip. So, this is similar to any coupling problem, because if you want to transfer energy from one system to the another system, you would probably align face to face and energy should flow. So, you can do this even for transporting water. For example, if you take two pipes and water is coming from one pipe, the other pipe with the same aperture, you can place it close to your inlet pipe, and whatever water coming out can be coupled to the output. And of course, you need certain force or pressure in one of the fibers, one of the pipes, in order to push the light, or in this case push water to the other pipe. So, if the force or pressure on one of the pipe is lower, what you do, you have to make them really close, right. And if there is enough force, you can still do it with larger gap. So, a similar kind of strategy is something that we are going to see now. So, in this case you have two slabs, or two, one is the source and another one is your chip, and one has, instead of water, optical field. So, you have optical energy from one. So, is it possible to transfer this energy from one to the other, right? And what are all the implications in doing that? Life would be very easy if it was like water, or even electric current, for example. So, electric current, you just touch two conductors and there will be a current flow. But in this case, we are talking about optical waves. So, optical waves are not easy to handle. So, they have their own characteristics. Unless these two systems are identical, right, we cannot transfer energy one to the other. This is again takes us back to our coupled mode theory. So, there we understood the phase matching is key to transferring energy from one mode to the other mode, or one solution to the other solution. Here we have two different systems. So, you want to transfer energy from one system to the another system. Then you have normal solutions for these two systems. So, we should look at what are those two solutions, how close are they, right, and what is the overlap integral. So, these are all the things that we should keep in mind when we talk about coupling light between two different systems. In this particular case, we are interested in coupling light between an optical fiber and a photonic IC, or this could be between an LED, so, or a laser diode and your photonic IC. So, let us look at how to visualize this thinking, and also look at what are all the parameters we should look at in designing such coupling and arriving at the limiting parameters. So, what is limiting our coupling, right? So, let us look at that. So, we shall start with a very simple structure that we would like to couple light into. So, you can think of a system like this. So, you have N1, N3 and N2, let us say, and the light is propagating in this direction, and this is X. So, I want to put the light into the system. So, I can put a lens here and I can focus the light into this particular thin film, all right. So, what I am essentially looking at is a system like this. So, I want to couple light into this waveguide. Okay. So, this is the mode that I am going to excite, and this would propagate through the system. So, this is essentially what I want, all right. And you can also invert this problem. So, that means I am generating light here. So, I might be generating light inside this thin film like a semiconductor laser, and I want to take the light out. Okay. So, it is a similar kind of coupling problem we have. All right. So, it could be from free space to our thin waveguide here, or it could be from the waveguide to the free space that we have here, and later on you might be able to couple it to a fiber on other systems as you like. So, when we are having such a system, one thing that we should look at is when I take a chip, right. So, let us say I have, this is photonic IC, I have optical fiber input, optical fiber output, right. So, there is an input and there is output. So, when I put about 1 milliwatt of optical power inside the system, right, and then it goes through this, and then I get, let us say about 0.8 milliwatts. So, there are 3 different laws that you can expect from this system, right. One is these 2 laws, what we call coupling laws. And then we could also have what is called waveguide and device laws, right. So, this both together, right, the coupling laws plus your waveguide plus device, all these factors together, right, is called insertion laws, right. This is general term we use. So, insertion laws, or you say circuit insertion laws, because it captures everything. So, input coupling, output coupling, and also loss on chip. So, when you take a system where your waveguide loss and device loss is very low, then your coupling loss is going to dominate, right. So, your coupling loss is very important. So, that is why we try to make the coupling loss as small as possible, so that we can get maximum light inside. You want to get the maximum light inside this, right. So, the coupling efficiency is very important. So, coupling efficiency theta is nothing but the ratio between power coupled into the target, right, power coupled to power available. So, this is our coupling efficiency. Similarly, on the output side as well, because it will be a reciprocal device, right. So, how do we calculate, or what are all the parameters that dictates this coupling efficiency? One thing there are 2 things, of course, right. One thing that quickly comes to your mind is from our coupled mode theory, right. So, there are 2 things we studied there. One is the overlap coefficient C, and then the next thing is coupling coefficient. Kappa, right. So, these 2 are the factors that we already know is important for coupling light. The same thing applies here as well. So, the overlap coefficient or in other words overlap integral is between input field and waveguide field or waveguide mode field, right. So, let us say E A x comma y is our input field, and this field could be from optical fiber or a diode source. And then we have our waveguide, right. So, field of the waveguide. So, this is waveguide mode field. So, let us say this is our fundamental mode, right. So, this could be for example fundamental mode. So, in that case this could be approximated to a Gaussian, right. So, what is our coupling efficiency now? So, that means you need to have the overlap integral. So, that is fair enough. So, let us look at what is that overlap integral. So, that is power coupled to the total power available here. So, that is all about the two fields that you have. So, that would be given by so this is the integral across this E waveguide x comma y to E A x comma y dx dy divided by E A x comma y. So, this is basically our overlap integral. So, how much of the field overlap that you have between the waveguide field and also the input field that you have. So, that E A x comma y could be from multiple sources. So, now this is there, and then another important factor that we should get here is also the reflection, right, or how much of power is going through. So, if I take two different, or we know this for a fact that if there is a refractive index difference n1 and n2, when light is impinging on this, light is going to do two things. One is refraction, another one is reflection. So, the reflected power is lost. So, we are not going to get it. So, we should know what is the reflected power. So, how much will be the reflectance of this. So, for that we can look at the two sources here, okay. That is the source E A and source E W G. So, these two are the two modes that we have, right. So, we can characterize this by using a very simple propagation constant of this, right. So, the propagation constant, so you have the input field, we talked about E A x comma y, right. So, this as a propagation, let us say beta A, and now the waveguide field. So this will have propagation constant beta Wg, let us say. So now how to calculate the reflection now? So we know both the betas, right. If you want to calculate the reflection here, so the reflection coefficient is given as so this is our reflection coefficient, or in other terms you could call this as effective index if you are coming from between air. So effective index minus 1 and effective plus 1 the whole square. Sorry, I missed the square here, so there should be square here. Okay. So by knowing the effective index of the mode that we have, we should be able to calculate how much reflection one could expect. Okay. So this is a very simple argument when you have from air, let us say. So this is coupling through air, then this is much easier to understand now. It is just n effective minus 1 divided by n effective plus 1. So now based on this we know the reflection, right. So as I mentioned, when you have a system you will have reflection and then you will have transmission, and once this transmission is known, then we should know how the overlap integral looks between the two fields, right. So between the two fields we should know what is the overlap integral. So we already know these two elements, we just have to put it together. So if this R is the reflection coefficient, then we know what is the transmission, right, and that is 1 minus R. So now we can put both this together to find the coupling efficiency. So now the coupling efficiency eta is given by the transmission coefficient, right. So we know the reflection here. So 1 minus R is nothing but the transmission. So this is nothing but how much is transmitted. Okay. So this is the transmission coefficient times our overlap integral here. So we can just write this whole overlap integral here, and that should give us the total so dx dy modulus square, and then we have the two fields here. So your waveguide field and your input field. So this will give us our field overlap, right. So this whole equation that we have is a characteristic of our coupling, alright. So this from here we should be able to find what the coupling should be. So there are two important things that is important here, the spatial profile, that means how the wave looks like, right, the field looks like, and also the propagation constant, which is captured by the reflection coefficient that we just saw, right. So the reflection coefficient depends on the propagation constant that you have, right. So that those two are the two important factors that we have. So now if you want to look at a system where we have let us say an LED put in front of the waveguide here, right. So instead of having an optical fiber, if we put an LED, let us say, right, how will the coupling look like, right. So that is something that we should know. So for that let us look at a very simple system where I put an LED, right. So we take again simple slab, right, and I am going to put a very small, let us say an LED structure here. So, in this case the LED is also a chip, let us say it is an edge emitting LED, right. So, now this is how my LED is. So, this is my light emitting diode and this is my waveguide, passive waveguide now. So, when the light is coming out of this, so you cross section wise it might look something like this, right. But then you should remember that this is again a flat thin semiconductor wafer, right. So, it looks something like this. So, if this is the case, the way that I have drawn is nearly the way that you would expect it to be, right, between x and y. So, if we were to put the axis, so this is z and this is x and this is y. So, if you look at the cross section of this, right, so you will get a mode that is elliptical in nature, right. So, you have elliptical light out coming from your, it will not be a Gaussian like distribution, it will be elliptical, but then that also suits our waveguide. So, our waveguide is also flat. Okay. But then the question here is what is the overlap between these two, right. So, that we will anyway capture with our overlap integral, but then before that the light that is coming out of an LED will also diverge. So, you have a lot of divergence that comes out. So, this is probably the radiation pattern, of our LED, right. So, now you can see here the light is emitted at various angles here, right, and similarly when it approaches our waveguide, right, it is also going to excite different angles, right. So, it is going to launch light at various angles. This is something that we know from our very basic thin film waveguide, understanding that not all the angles are going to be propagating here. So, you have a critical angle, only light within that critical angle will be transmitting, right. So, the way to look at that is you have an accepted angle, acceptance angle here, right. So, there is a cone here. So, there is a acceptance cone, only within this cone you are going to get all the light propagate through the system, otherwise the rest of the angles are going to be radiated. So, all this is all radiating outside. So, you should have this particular angle here for it to propagate. So, again whatever total light available from the LED here may not couple into the waveguide here. So, only a subset of that is going to couple, right, and that the brightness of our LED, that is from on the left side, can be given as the angle, the exit angle that we have, right, from this light emitting diode. So, it normally follows Lambertian source format, and that is what is shown here. It will be 3 dimensional in nature. Okay. So, now we can write the power, right, that is coupled into this system, very simple system, by using what is the pattern, the output pattern of the LED along with our waveguide dimension we have, right. So, in that case we can write the brightness of our LED as a function of theta and phi. So, this is how the light is distributed, right, and that is given by very simple theta. So, theta is the angle, the divergence angle that we have, and this can excite different spatial modes that we have, different thetas we have, right. So, let us look at what is that overlap integral is going to look like. So, we have kept your LED very close to this, and we want to understand how much power will be carried out through this, right. So, we can, since this is associated with the 3 dimensional solid angle here, right, we can use cylindrical coordinate system here. So, the power coupled, right. It could be written as, if you consider the circular symmetry here, right, you could have a radius along the radius and along the angle here, right, will be given as some theta max, or theta critical is what you have, cos theta sin theta d theta into okay. So, this is the LED part, right. So, what is the LED angle of illumination that you have. Okay. So, this gives you the capture or the power that that is coming out of this system. Okay. So, now though you have this power coming out, we should understand that it all depends on the numerical aperture of this. So, basically what you end up with is, though you have all the power that is required, you only get the power that is within the numerical aperture of your waveguide, right. So, your numerical aperture here becomes very important here. So, you can simplify this, right, and the power coupling will be pi squared r square times b naught into Na the whole square. So, there is a disclaimer here, right. So, we are considering a circular symmetry for this particular waveguide, right. So, you have a power coupling where you it is almost like a fiber, right. So, in this case it is like a fiber, but then you can, instead of r, the reason why I am doing this as for a circular is it is rather easy to do the math for this, right. If you want to do it for a rectangular waveguide, then you have to do for both x and y. Okay. So, everything remains the same, but the integral will be along dx and dy, alright. So, that is the only difference that you will see from this, and you can approximate this if your x and y are identical, right. That means if they are square, right, then you can use this approximation as well. Okay. But nonetheless this is something you should keep in mind, that this assumes that there is a radial symmetry here. Okay. That means it is all circular in nature. So, this is how you can arrive at the power that you can couple between a very simple LED and a fiber for all practical purpose here. So, which has a circular symmetry here, alright. So, and then if you want to couple light between two different waveguides, right, as I mentioned, you need to look at the propagation constant and finally reflectivity and so on. In this case it is all taken care because this brightness is given by the source, right, what is the source that we have, and also the Na tells you about the receiving end. So, the power coupling is taken care with this very simple relation, alright. You can also elaborate this discussion and continue it when you have a lens based coupling, for example. That is the first drawing that I had. You could have this lens based coupling, right. What happens in that case? When you take a lens, then you should know what is the size of the spot that you are going to take. The spot size should be approximated. Based on that spot size, you should be able to find whether it is overlapping with the mode here. So, you will have a Gaussian mode at the end, and you will follow the same discussion here. So, you will have a Gaussian mode along with your input field, that is your mode that you want to excite. This could be fundamental mode. So, you find the overlap between the fundamental mode and your the spot that you have, the Gaussian spot you have. Just to give you an example, how much the reflection will be in a simple system, for example, right. So, if you take a simple fiber, right. So, I have an input fiber. So, the fiber has silica, right, this is all SiO2, and N effective is approximately equal to 1.45 or 5, let us say. Okay. So, I want to know how much of power could be transmitted and how much will be reflected, right. So, here you can easily calculate this by calculating this factor, and it will turn out that the reflected power will be about 4% coming from this reflection, and the transmitted power will be 96%. So, even when you have a fiber, it is not 100% of the power is available. Okay. So, you will only have 96% of the power available when it comes to coupling between the fiber and some other system, let us say. But now, if you are going to increase the refractive index, right, if you are going to increase the refractive index from 1.5 to let us say 3, right, then you can quickly do the calculation and then see it is not going to be 96 anymore, right, it will be much lower, right. So, the higher the refractive index contrast, right, between the systems, right, then your reflection is going to increase and your transmission will reduce, and this is a challenge that we have when you take high coupling between high refractive index platforms. For example, coupling light into silicon or silicon nitride is challenging compared to coupling light into a circuit with silicon dioxide. Okay. So, if you there are silicon dioxide, there is silicon nitride, and there is silicon. So, silicon dioxide refractive index is 1.5, and this could be 2, and this is 3.5, and the coupling efficiency, this is for end fire, the edge coupling without doing any fancy. You will have the highest coupling here, and you will have a bit lower here, but here the lowest. Okay. So, the coupling efficiency reduces based on the refractive index that you have between silicon and also with the environment. Okay. So, that is something we should keep in mind when we are designing for coupling. So, with that we have understood coupling between coupling light into the waveguide from a lateral side, right. So, you can couple the light from lateral or you can couple from the side. In this discussion we saw what are all the implications and design criteria we should take when you are coupling light from the side. So, with that we conclude this section on coupling light into the chip. Thank you very much for listening.